Okay, so end of the day here, we've had a great workshop, I think, for the day. We had some awesome talks this afternoon. Thank you to the speakers. And yeah, what we're going to do here is sort of pick up the conversation from earlier today. We can fill people in if maybe you weren't here. We had some big picture themes around, you know, what does a robot foundation model look like? What's the path to general purpose robotics, and some topics kind of in that area. We had some great talks this afternoon. We want to start here with some talks sort of specifically for these four speakers. So again, so Aleksandra, Oliver, Georgia, and George. So if there's questions from the audience, sort of from the specific topics in the talks, let's start there. And then after that, we can just kind of do more sort of big picture, you know, what's the path type of questions back and forth. So first from the audience, if there's any questions for the any four of these speakers here. And also, since we have two online, if you either want to grab a mic from me to ask your question or try and boil it down to such that I can restate it quickly enough for the speakers, that'd be great. So let's start with one here.
Thanks for the talk. So I have a question for
Georgia.
So can you go into a bit more details on the NILP, so mixed integer linear program formulation for the that grasping task?
Mixed integer linear programming, you mean, for the assembly?
Yeah, for the assembly.
For the assembly.
Yeah, sorry.
So in the mixing, so consider that we have like a RSS problem where you need to fill a volume with some objects, and you need to find basically the combination of these objects in such that you can fulfill this volume. Now, to solve this mixed integer program, we basically gave like 1, 0, 1 whenever you, so we voxelize this volume. We have these, as you saw, Tetris-like objects. So for sure, we have all these, you know, easier objects to work with. We assume that all of them are constructed by specific building blocks that are these cubes. And we take this as a primitive shape with which we help voxelize the respective volume that, you know, we abstractly take several lines, create like a 3D structure, and we say, okay, this is what we need to fill in. After the voxelization, basically the MILP will try to find out for the different objects and with different orientations, whether or not they can fulfill or not the specific voxels, and it will take +1 whenever it gets in and 0 whenever it is outside, without taking any more assumptions, whether it is in the air, whether it, you know, does collisions, just needs to fulfill it. So we basically abstract, you know, way more high level execution compared to the real world, where in the real world you were actually observing in the environment the collisions, whether, for example, one grasp was infeasible, you know, to execute and so on.
Other questions for the four speakers from the afternoon?
Thanks. Question for George. You were talking about the low-level abstractions, sensor mode abstractions. So I was wondering what you think about going even more low-level, so to mimic the intelligence that's really also in our bodies and animal bodies, so reflexes and synergies and energy storage and these kind of things.
Okay, so I think the analogy breaks down when we get to like energy storage and stuff like that, because batteries are better than food. Well, maybe not better, but more convenient. So
Less delicious.
Yeah, so less delicious. That's right. Yes. So I think it is going to be the case that we're going to have to build in a lot of stuff. And, you know, reflexes are there because, well, there's kind of two roles, right? Reflexes are there because they bootstrap learning when you're a baby. And reflexes are there to, you know, stop you from like careening off cliffs and stuff like that. I don't see why that wouldn't fit in. I think in real life, we're going to have to build in a ton of stuff on a robot because robots interacting safely with the world is really complicated, right? It's just, and safely and sample efficiently is just not a thing that you can do by slamming an MDP on something and learning. You're really going to have to think quite hard about the embodiment bit. So yeah, I think it's going to be complicated. But we all do that anyway, though, right? And we just do it in a once-off ad hoc way. When we build our system, we sort of build in some breaks, and someone sits there with an e-stop. So yeah, I think it would be great to think about that more systematically. I'm not sure that I'm equipped to do it, but it would be cool. Does that answer your question? Yeah. Okay. Thank you.
Thank you. So I have a question for Aleksandra. Aleksandra, you can hear us, yeah. You showed this very nice, you called it code. I forget what it was, but sort of like generating environments basically. And for these sort of like navigate the web tasks, this kind of like learning the curriculum itself seemed to be very helpful for learning these like very complicated web navigation policies. It was making me think of earlier, Mark was, one of our speakers from this morning was asking about like, hey, how do we come up with all the tasks? And I was thinking of like, you know, basically a question for you, Aleksandra, do you think we can kind of use this, generate the tasks and generate the environments type of frameworks for these more kind of embodied robot tasks, as well as these, you know, web navigation domains? And how do we do that?
I love that question, because part that I didn't mention in the talk today is that really task definition. And I know there are different lines of thought and so on, but and this is a panel, so it's supposed to be somewhat maybe controversial, but I'm a big fan of actually understanding what problems we're trying to solve. Right, and what is the task structure and so on. So one thing that we did in paper that kind of is behind the G-minimal, which is the environment that generates these tasks, is that we formalize them as Petri nets, and specifically as a workflows and then establish that there is one-to-one correspondence between the Petri net that defines the task and specific POM MDP. And what that means is that if we want to look at the generalization, these particular Petri nets and so on happen to have a structure, right? And we can define this structure through rules, in this case, and then we're after solving the whole basically induced set of POM MDPs that are induced from that structure. Some things that we found through trial and error there is that specifically, we're looking here at the tasks that are induced with a fixed set of primitives with this structure that are solvable. Certain tasks are not solvable. And maybe some curriculums are going and looking into find me the solvable tasks. Third class of tasks are the open-ended tasks. These are in the web navigation context and so on, it's like, I'm done with the task. It's very clear end. But there are open-ended tasks in Minecraft environments and games where kind of your goal is to just maximize the value and can keep racking the points, right? And these methods don't work, or this particular method does not work. But if we kind of challenge ourselves and think about what are different task structures, I mean, we'll get the answers how to solve them.
Nice, thank you, Aleksandra. I saw George nodding his head. I think he was happy to hear you talk about structuring POMDP. So, another question from the audience. We have one right here.
Thank you, everyone. I have a question for George. So I'm super on board with learning abstractions to be able to speed up learning, speed up planning and everything. That's been my experience as well. My question for you is, how would you handle learning the wrong abstraction / updating your abstraction instead of like learning it from scratch when you change the environment or change the, the task, the subset of tasks that you're looking at and so on?
Thanks. That's a great question. So part of the work that my lab's put in is to try to understand what it means to be the right abstraction. So in our case, what it means is that, just to get annoyingly technical for a minute, the thing that we want to be able to evaluate is the probability of a straight line plan succeeding. So if you like run this skill, then that skill, then this skill, then that skill, then this skill, what's the probability that you can run those in? And our abstractions are constructed to be sort of correct by construction, right? So there is a classifier or a distribution of states that you could learn that would let you compute that thing. Now, of course, in practice, that's not the case, right? You go get some data, maybe the world changes, maybe your data is not sufficient, and you learn a distribution and it's wrong. But what's nice about having the kind of formal semantics behind each abstraction is then if you take the actions and something surprising happens, you can kind of attribute the error to one of the distributions, then go and refine it, which is very neat and is not a thing that we had before we defined the kind of formal semantics that way. Does that make sense? So because everything's kind of tightly knit together, you can recover by slowly shrinking things. And we haven't done this yet, but I think the default mode should be abstractions are always wrong. Like they're just tending in the right direction is usually enough to make things work. Does that make sense? Cool, thank you.
Do we have a question for Oliver specifically from the audience? I want to bring you in, Oliver. I have a question for you, but I want to see first if we have one from the audience over here in the corner.
I had a question, Oliver. You had a lot of focus on object-centric controllers. I was wondering if you could speak a little more about your, sorry.
Hi, Oliver. You spoke a lot about object-centric controllers, and I was curious if you could talk a little more about what your thoughts are for appropriate object representations for those controllers.
That's a fantastic question. So we've been focusing a lot on sort of key points on objects. So I'm trying to find which points are sort of semantically meaningful. But I think that the real object representation that we need is going to ultimately be some kind of a hierarchy. So I often like to think about this problem of sort of scooping a bunch of coins into your hand from a table. Where originally you have a bunch of individual objects, you scoop them together, you suddenly treat them as one big sort of mass object. You have a table that's a single object, but you have to break it down into sort of a small part of the table. And so I think this idea of being able to sort of move fluidly along this hierarchy of different object and part representations is something that we as humans do very naturally, and something we haven't really gone enough detail in the robotics, I would say. But yeah, I think having I think it's an excellent question. And I think you can use some of these sort of ideas of object-centered controllers or at different levels of that hierarchy, and then having the action sort of fluidly adapting as well.
Thank you, Oliver. So maybe we can zoom back out a little bit and zoom back in. I want to go back to some of the themes from earlier this afternoon, including, and I think we can start out by way of a question here, going back to the theme of foundation models and do they have a role in robotics, specifically not just bringing in LLMs or other foundation models from other fields, but sort of specifically like a robotics foundation model. What does that look like? And actually a question for you, George. You had I think this is fun to think about. You had a comment around if you want to minimize sample complexity, then minimize learning. And I think certainly, a lot of us that resonates because we know that, like, yes, if we have like really nice structure and we only need to learn a couple things and we can nail the problem. But then I think it's also interesting to think about, we see the success, at least by some measures, over in the language domain, for example, and very large language models, they're sort of like all the learning, and then they can actually be very sample efficient at learning new skills through the magic of prompting. And you give it all the text on the internet, and then you just give it a few examples of how to answer multiple choice questions, and then it can nail your SAT. So do you think that transfers over to here and sort of raises the question to minimize sample complexity? Should we minimize learning or go all in on learning and figure out how to prompt? Or does the lesson from language modeling sort of not translate over to robotics, you think? What do you think?
So I don't think it translates, in part because having all the text on the internet is a bit of a special case. But the other problem is that you don't get an interactive text on the internet, right? So it just all happened and you get to watch it. This is like watching expert demonstration trajectories, but you can't actually get everything you'd like to get out of that. And this is why sometimes it fails horribly, right? Sometimes it will just say stuff that doesn't make any sense. In the robot case, robot data is really expensive. You really have to do the interaction in most cases. And so I don't think that naively applied something like that would work. However, these models are really powerful. And so if you could find ways to kind of use them to compress lots of experience that you've got, for example, like learning a quantitative physics kind of local map of actually the type that Georgia did, I think is a really good way to say, I expect the world to work like this for the next 10 seconds. I don't have to learn that every time because physics ports. And so maybe I don't have to do from scratch reinforcement learning. Like that seems like a natural way to bootstrap.
I don't know if we need a foundation model. For sure, I would imagine that in the near future, given that there will be different types of robots, so they will have different embodiments, you would like to have, I don't know how to frame it, like a World Wide Web or something similar that could collect experiences and, you know, inform somehow over the experiences of one robot and potentially be transferred to another robot. Of course, the representation is the one that we have to abstract, because in the end of the day, you will be bounded by the robot that you have and the structure of the robot that you have. So, for example, what you saw in my work, it was only for this structure of the Tiago robot. Then for another robot, we will have to train a different model that it's the hardware, the design of the robot, and so on. And for the language model, I wanted to say something, because I am also like working in this direction a bit, trying to extract some sub plans from humans. From what I consider it is like a common sense. It's a different way of somehow encoding knowledge bases into a super huge transformer network. And then when we do prompt engineering, it's like looking up, you know, how to query a database. Because if in the end of the day, it was easy to collect all this knowledge of the World Wide Web and do the querying appropriately and search for all the entities and the objects, we would get something similar, which is impressive, of course, that we can do it with a language model. But I would also like to point out that I wouldn't like to have for my generalist robot billions and trillions parameter model that I have to query every time. I consume, I don't know how much energy to query it and so on. So I think we should take into perspective also these sub problems into account.
Yes, definitely. Here's maybe a different phrase, but question I'm curious for the panelists. Maybe we don't need a foundation model, but the question is, if for some magical reason, so this is very much one of these sort of like, you know, very hypothetical questions, but if every bit of data from every embodied robot that's people have ever been doing research on over the years was just magically available, all logged in, you know, some nice consistent ROS format or something, and you just had access to it. And not only that, but you had great documentation that could be parsed maybe automatically on what was going. That's the least likely thing. Data from all the robots, everybody's like, I don't know. But then everybody's like, documentation on all of them? Impossible. But we can imagine. So imagine this is the case. You have data from all these robots, and it's just all logged and it's all sitting there. And the question is, you know, would you use it, or would you just, would it just sit on the servers and you would not want to use it? Or and of course too, maybe you don't want to like train some model on it. Maybe you just want to validate some algorithm with the data or something. Yeah, what do you think?
I guess
any of the panelists.
Oh yeah.
All right. You have a take.
Well, I was kind of thinking about George's sort of that substrate at the bottom. Kind of, because I mean, when I was thinking about this kind of data, I was thinking like, okay, are we going to have sort of a one childhood sort of shared amongst all robots, where like, okay, they're exploring, they're learning about the basics about how the world works, and then sort of, at some point it's like, okay, they've grown up now, and now they're going to have to do, go out and get a job, I guess. And I can imagine something like this, sort of, taking all that information and trying to create something consistent that's sort of shared amongst all robots in that form. I think, having it all available, you're going to get something similar to like with the internet right now, where there's just so much information. It's more of a question of how do you get the information that you need. So you do need that somehow to compress it and find out what's actually relevant. But I could definitely see a use for that. I think, transferring between robots is definitely something that is going to be useful. And as we also talked about with this idea of abstraction, that if you have a certain amount of abstraction, that's also going to make certain information easier to transfer between different embodiments.
Can I add my two cents?
Yes, yeah, please.
Yeah, so I can go back to answer the previous question, because that's something that I'm actually thinking a lot recently about. We people are very good at producing language, lots of it. And there are massive amounts of data, which when we translate to robotics, I am not.
It's just like a conference ceremony. Like I might get some.
Tony, I think you need to mute.
I am not sure if we can kind of dig out as much data with the robotics. And similar point to that is that robots are systems and they are generally autonomous, so they can't run on the data center, or at least not easily. So these models that kind of run on actual robots, especially they're like compacted UAVs and so on, need to be really compact. So there are challenges, right? And so I don't think it's one-to-one. It's just easy. Let's kind of replicate what large language models did and so on. That said, we have found recently that generative models are producing and generating robot-specific data for training, and we can actually get away with surprisingly coarse models that are, or the environments, right, and data with that we're getting pretty much for free. So that's something to think about. In terms of foundational model for robotics, and your second question, would it be interesting to find that kind of have a unified interface and we can collect all the data and train? I think that's fascinating. I think it's the direction we absolutely should do. One thing that surprised me with large language models is, and again, this is through the web navigation work, there is a third-party nonprofit there that maintains open data set of the snapshot of the internet. Billion web pages there that are sitting there in the open source and anybody can use to train a model or whatnot. Imagine if robotics had something like that. That would be amazing. So I'm a big fan of having data, and then we can figure out how to be sample efficient with the data.
That would be amazing. Are you talking about, it's like the Wayback Machine or something it's called, just like these free archives of internet pages?
It's Common Crawl.
Common Crawl. Common Crawl. Yep.
Yeah.
So, okay, excellent responses. I want to go to a question for George, which sort of fits into the sort of, how do we do the big picture here? You had a very nice, like, yes, POM-DPs are excellent, and we could just do RL, and maybe the challenge is sample efficiency or other practical challenges there, which are, especially for real world robotics, are quite hard. But also just a question too around like, a little bit of some of the problem space that even that very general formulation doesn't quite answer itself is, you have this sort of like derived state action abstractions, which are simplifying that raw state actions of the robot. But two questions. One, who decided what the embodiment, the state action spaces were in the first place? How do you solve that problem? And then also to the rewards, as you called out, where the reward functions were assumed to just be sort of given. And so how do you think about scaling reward learning, which was a question from this afternoon too?
Okay, so on the first part, I just bought that robot and it came with a state and action space, right? So that was the
sure. But then is that the robot that we achieve? As you said, the existence proof of general intelligence is only embodied. So is that the robot that's going to be the first, general intelligence robot, or does it need to be different in what way?
Well, not that one, because all existing robots last like 6 weeks and then they break. So no robot that exists today is likely to get to out of just sheer unluckiness. I do think, one of the things that we're kind of going through in my lab is learning motor skills, and like robots, have a tendency to tear their own fingers off when they're interacting with stuff. And so you have to put a lot of software between the raw motor space and that thing. So you have to do some engineering there. And I'm not convinced that the engineering ports that much between robots. I think one day we'll get a robot that's good enough and we can just kind of run with it. For the who decides the reward function, I think people should decide the reward function. I think, people have a motivation system and we generate our own reward functions, but actually for robots, it'd be nice if we gave it to them. And then there's a question of what that should look like. So I haven't done a ton of work in this, but Stephanie Telex's lab, some of her students are here, and Michael Lippmann's lab have thought about how you express reward function in LTL, which is a very natural way for people to express reward functions, linear temporal logic, which is like it's like a nice way to write, like do this and do this while never allowing this to happen. And eventually this should happen. You can kind of write really nice temporal expressions that way. It's very natural for people to pick them up. And what's nice about LTL is you can build a sort of automaton from it that's quite similar maybe to what Alexandra's building with a Petri net. And that's very structured. So actually the reward function that a person is giving the robot is not actually a black box that you only experience when you get to a state. It's actually something you can take apart from the instruction. You can understand the structure of the instruction. You can bootstrap learning. And I think that makes a lot more sense than following a robot around with a good robot button, right? Like that doesn't feel like the right thing. So actually, I think our instructions to robots are going to be quite rich in stuff when we get to the right formulation. Does that make sense?
Yes. Georgia, how about for you? In your talk, you had a very nice sort of like the path towards general purpose robotics, a few different main areas where, you know, you and your lab and others have been making progress on. In terms of like, you think the main limiting factors right now, like, you know, so you had a few different areas. What are the ones that, or what is maybe the thing that you feel the field is sort of most limited by right now? Or put in other ways, like if somebody could just provide you a solution for some sub problem of the overall robotics problem, would you be most excited to just grab onto that solution and then keep going with the rest of the overall robotics problem, you think?
Okay. I think for sure, I would say still on the path of perception, of embodied perception. And how do we assume, for example, that usually we have like external perception systems that can capture the world, we can abstract, in the end, everything is upon DP. How do we create these kind of complex representations of the world such that the robot has kind of a world model? So even if I have a plan or like somebody tells me, you know, you have to make a coffee, I know that there exists a mug for sure in my world and I have to find it. And I wouldn't expect my robot to just go around navigating, trying to find a mug somewhere in the, you know, to locate it and say, this is the mug, this is a mug, take it. Like we know where the mugs are. We have this concept. So I think like representations in the end is one of the biggest problems, abstract representations, because you don't want to be bounded by just an image of something that represents the world. This is the first thing. And the second thing, as I said in my talk, like we didn't touch on it so much, it's safety. And safety, it's on multiple levels, like safety for the world and safety for the robot. Because we can imagine that these robots are, even if they go out in production and they go into our worlds, they will still be expensive. It will not be so easy to have one of them, I would assume, at least in the beginning. But then you wouldn't want them to break and you wouldn't want them to break the world. So actually integrating the constraints in an effective way. And how do you perceive the objects? And I think Mark Toussaint also talked about it. How do you perceive the constraints and integrate them? And yeah, but I think one part comes also from the robots themselves and the way that they are being built, because you would like the robots to be more compliant when they are in the human body is compliant. So the embodied intelligence, it's not about the intelligence on the high level, but it's also the embodied intelligence of the robot as a structure on its own. How does it perceive, for example, the collisions? And there is work actually towards this direction. So we have to take into account also the morphologies and the capabilities of the robots and whether or not they can effectively comply with the environment when there is danger.
Awesome. A lot of nice topics in there. I do want to open it up to the audience if there's any questions for, I think we have time for maybe a couple questions and then close out here. Why you have a question?
I have a meta-level research question, which is that in the presence of these foundation models, what should the role of academia and industry look like? What should the relationship look like when only one side could produce these huge enablers to robotics? And that it's not just the difference between a few percentage points on a few benchmarks, but that this rule of scaling up large language and vision models, it's able to achieve abilities that smaller models at smaller scales can achieve.
Maybe before I answer, I will say that there's been some like open source reproductions
Yeah.
of, you know, for example, Clip has been matched by fully open source compute and stuff like that. So it's certainly advantages of industry, but I don't want to set the stage that like only industry can train sort of, you know, relevant stuff. But it's a great question. Yeah, what on the sort of overall in these kind of like, you know, tons and tons of data to the extent that people want that, or maybe they don't. But in this regime of tons and tons of data, train big things. Yeah, I don't know. Answers from the audience on the role of industry and academia.
Yeah. I can try that because again, over the last 6 to 12 months, we've been playing a lot with the large language models. So maybe that's kind of an equivalent to a certain extent. Since they're narrow in what they do and they provide a good utility, so they're not state of the art in any kind of specific test, so there's lots of fine tuning, and then they're very useful tools. We found it across several projects that they're really good. Like I even mentioned that on the navigation instruction work. The large language models are there to translate instructions to different languages and so on. But there is still a fundamental question there around how do you find the right landmarks, right, and the right pieces and so on. So if you kind of extrapolate these findings to hypothetical robotics foundational model, I expect that at least the first foundational models would be very specific to a certain task or maybe to a certain robot and so on. So there's going to be plenty of work then. Okay, we can use this foundational model as a building block, as a tool that then can be either put in a different context, right, or built around and so on. That's my take.
Thanks, Alexandra. Georgia, yep.
As a young academic, I will say what I envision, because I mean, I think, I don't know how it is in the US, but in Europe, I mean, we don't have all these resources to train like models with billions and billions of parameters. So for sure, this is a kind of a problem. But I think that where academia can really contribute is into creating the consistent benchmarks and rules to actually test what the industry is developing. Because I mean, different labs from the industrial side, they are creating their different works. We see all the competing, you know, one week we see DeepMind, then you see Google Brain, or then you see whoever else. I mean, okay, now DeepMind, they are the same. Okay, I would say Amazon. I will not start like talking about all the different people that, like, for example, deploy this kind of foundation models and so on. But who checks them? Like, they create their own benchmarks. You don't know exactly how they do the evaluations. You don't know exactly how many things they don't say in their papers, because I mean, it's also in the interest of the. I mean, they are companies. They want to promote themselves. They want to promote basically a product. So who creates the rules about understanding whether or not, you know, your product will actually promote the overall objectives of research? Because, I mean, they do research and development. So in the end, they want to develop something, and you want to ensure somehow that what is being researched, it's actually in multiple levels, ethical, not biased, researched with specific objectives. And now we say this, and I have to say that making common benchmarks for robotics, it's a long problem on multiple levels, but it's something that in the end we have to address. Like, we have to bring together academics to create this kind of brainstorm, and together with the industry, obviously, to create this kind of benchmarks and push forward in the future also the research that the industry is doing.
Yeah, and to go along with that, Georgia, like, in addition to helping evaluate, like, sort of when somewhere comes up with some, you know, new big fancy solution, like sort of helping validate and evaluate, also, I think there's a great analog for the need for more high quality, robust, diverse evaluation protocols and data sets, or whatever they are, in robotics. And over in the language modeling domain, for example, when all these new results are released and like, oh, our model is bigger and better, and so they're reporting results on all these standard benchmarks, and most of those benchmarks came from academia. And so even, you know, I don't know, maybe sometimes people think of like, oh, like the thing that, you know, the main part of the solution is like training the thing, or if, you know, if you're going to train a big model. But if you trained a big thing in robotics right now, it would be a lot of work to sort of show that it's relevant and actually sort of solves an interesting amount of things. Maybe that's certainly at least one way in which I think academia can be helping contribute. Other thoughts, Aleksandra and Oliver?
So I completely agree with Georgia in terms of the selecting the benchmark, creating the benchmarks and so on, and feels like a good time to do a little plug for a workshop on Friday for robotics on cloud. It's supposed to be precisely discussion around what are the requirements for the large open source benchmarks in robotics and tasks and so on. So stop by.
Aleksandra. Let's maybe do one last question from the audience. Sorry, George, you want to chime in?
Okay, since there's a panel and I get to be a bit controversial.
Yes.
Okay, so I wanted to say two things, both of which are that the situation is temporary in some sense. Okay, the first reason that it's temporary is like hardware is getting, there's kind of two advantages to being an industry. One is you have a lot of computers, and the other one is you have some engineers who can help you out. Okay, and progress will kind of slowly raise those advantages. They're temporary. Eventually we'll get faster GPUs and all that stuff, and it won't be an issue. And this may take a while, and maybe it'll take too long for your purposes, but it is a thing that happens. Okay,
don't fret.
The second one is that it's temporary in that, like, in the natural order of things is that academia funding is basically socialized, because it's after basic scientific questions and it's very far ahead and very blue sky and very low probability of working, roughly speaking, right? And there's supposed to be a funnel where, like, we do the sort of crazy out there stuff, and then over time it sort of filters down and coalesces into concrete knowledge, and that is a thing that gets into a company's R&D, and the company R&Ds for some number of years, and then that turns into a product, right? And that funnel is supposed to be like 15 or 20 years. So now we haven't delivered a moment in world history where, and the reason that it's socialized is because there's such a high risk and such a low probability of success, but such a high utility. I mean, think about the utility of the internet, right? I mean, it's like tens of trillions of dollars, right? And if you go back to the 1950s when they were studying, it was completely crazy that something like that would happen. So one answer is, if you feel like you're competing with those people, you're not thinking far ahead enough. Okay, so just assume all that stuff works. Then what happens next? But another thing is, we do live in a weird kind of time in history where companies are the size of countries. There are a few companies that are basically outside of capitalism because they're so big, right? And therefore they can basically run a socialized kind of research thing, chasing big questions. Those situations are not stable. Okay, and Bell Labs was that way for 20 or 30 years. It produced large numbers of Nobel Prizes. It was amazing. But ultimately in capitalism, you don't just get to do stuff for the love of science, right? Eventually you have to use it to make money in the limit. And eventually that stuff is going to have to start to turn towards products. Maybe not in 5 years, maybe not in 10 years, but it's going to have to. And in academia, you're free from that. And I promise you, and my university is 300 years old, I promise you in 1,000 years from now, it will be here. And I can promise you that in 1,000 years from now, Google will not be here, right? So you think really, I mean, okay. An open question is in 50 years from now, if it's going to look like it looks now, right? And so just think further ahead, chase bigger things, and that's where the interesting questions are, in my opinion. And then people at companies, Aleksandra, should give us their models so we can just use them and build cool, fancy, crazy stuff. And if it happens to work, then you should take them and do cool stuff. Right? That's don't forget that, Hinton was tenured at Toronto, and there was like 20 years where deep nets were the uncoolest thing you could do. And no one would, I mean, industry funding wouldn't touch it, right? It was not. There were several years in Europe where there were no papers that contained the word neural networks, right? But there was a person with a tenured position who thought it was the right thing and spent 20 years fixing it, and now we are where we're at. And that happens in those kind of unique situations because universities are structured the way they are. So you want to be that person. You want to think that big and that far ahead. Okay, thank you.
Thank you, George. Let's do one more question. Okay, we have one here.
Yeah, just back to this backbone question. I was just wondering, what's your opinion on what the level of abstraction should be if something like this were to exist? Because I guess it could be something along the lines of just affordances in an environment, which might then transfer to many different embodiments, but then you need local models for each different embodiment. Or it could go down all the way to actions, which would make it much more difficult to transfer. So any opinions on that?
So my unifying principle is there should be as many abstractions as you can get. There should be many, many layers, and the robot should choose them at runtime. So we have to let go of the idea that there's one true one, right? There's going to be lots of them. And the only design criteria is that this thing is likely to be useful at some point. So you should build them at all those levels. And as long as you don't induce such a penalty in choosing the abstraction that it becomes not worth it. That's what I really am envisioning, layers of this thing, and the robot dynamically deciding whether it wants to treat this as a sort of object level thing or it wants to learn pixels. And this is what kind of gets you out of these awkward questions about like one model having to do everything. One model doesn't have to do everything. There's no way that there's a single model like like first order logic doesn't capture all the problems, but neither does deep Bayes nets. None of these things capture all the problems because you can't capture all the problems, right? Unless you go to the lowest level of POMDP. So the question is, can you build 10 abstractions that will cover 80% of your use cases? If you can do that, then you're winning. Does that make sense?
Yeah, makes sense. But I guess then again, the question is, how do you define these levels of abstraction?
Oh yeah. That's going to take a couple of drinks, but we have a plan. So maybe later tonight here.
Which is maybe a great transition to further discussion can be had over drinks later tonight across the city of New York. Maybe we can thank all of the panelists for their time and their talents. Thank you so much.
Yeah, thank you very much. We will now